everyone, I'm Wenjun, a faculty at Yale. I'd like to talk about Mistify today, a recent work we published at NSDI this year. These days, there are many smart devices around us, collecting or generating lots of data. Increasingly, there's lots of interest in running on-device inference over these data to generate insights. Now, given these devices tend to be very small and resource constrained, we want compact but still accurate models for those devices. So, where to get these models from? A common practice is to start with a large pre-trained model and then tailor to the deployment setting. Quite often, that means shrinking a large model to something smaller. There have been a lot of algorithms for that purpose. But that's not it. The actual process is still very involved. First, you need to implement the algorithm, which may require laborious and, more importantly, error-prone manual effort. What's implicit is also that you need to understand both the algorithm and the runtime constraints. That can be a lot of expertise involved. Then, the actual search process is very expensive, taking a lot of time and also a lot of memory usage. And all of that just for one target. Now, if you want to run an app on diverse hardware, you may be looking at very heterogeneous hardware capability that can vary by orders of magnitude. The application performance requirement may be very diverse as well. Here are 3 examples, all based on vision. But given the nature of the application, the latency requirements can also vary by orders of magnitude. Then if you have a long-running application, you also need to look at the runtime dynamics. The requirements may change over time, and depending on what else is running on a device, the available resource may change as well. So, to address all of these issues, we built Mistify, which is a system framework to automate DNN porting at scale. The idea is to decouple the DNN design and deployment stages, and then in doing so, we can reduce the amount of manual effort involved and also the computation overhead. So if you take an ecosystem view, I'm using TensorFlow as an example, then Mistify sits between the design stage and the deployment stage and acts as an intermediary between the two. We adopt a number of techniques to address the challenges mentioned before. First of all, we provide an abstraction called adaptation executor. Essentially, we provide a number of APIs so that you can implement the tailoring algorithm generically without tying this to specific deployment goals. This is a way to essentially decouple the design and deployment stages. Now, let's say you want to adapt the original DNN to a number of devices represented on the lower left. So you can describe this in terms of number of parameters to describe the model size, or the number of flops to capture the resource constraints. Now, if you were to deal with these 7 goals independently, there are actually a lot of repeated steps. So doing them individually is very inefficient. But then if we look at these 2, goal 2 is more constrained than goal 1, which means that if you start from the end result for goal 1 instead of starting from the large model, then it's going to be more efficient. This is the intuition behind what we call collective adaptation. So essentially, instead of dealing with 7 goals individually, we sort of merge them into a tree so that you can only use 3 processes to run through all 7 goals. Now, for the runtime, we take different action in the both foreground and background. In the foreground, we basically generate multi-branch DNNs, each branch corresponding to a different resource specification. So in practice, you simply pick the branch that best match the resource specification, and this switching is very fast. In the background, the system initiates re-adaptation on demand. For example, now we want to add another goal. Then this is inserted into this configuration tree earlier, and then a new model is generated accordingly. So this hopefully provides an overview of Mistify. There are a lot more details of both the system and experimental details in the paper. We have open source the code. The link is also available in the paper. So thank you for watching the video. I'm happy to take questions now. Thanks.